Right. Well, thank you so much. So I'm a PhD student at the University of Minnesota. I know it doesn't say my affiliation in the program. So I'm advised by Larry Edwards, and for those of you in the biz, you probably wonder why I'm up here, because I'm not a meteorologist. In fact, I spend a significant amount of time drilling tiny holes in rocks to understand past climate change, but HYSPLIT has an application in a lot of fields, and there is a real need for efficient, repeatable workflow in HYSPLIT. So what is HYSPLIT? It's the National Oceanic Atmospheric Administration Air Resources Laboratories Hybrid Single Particle Lagrangian Integrated Transport Model. There are two primary simulation types that you can do with HYSPLIT. One, which I'll give an example of and then never mention again, is the dispersion simulation. And then the other, which PySPLIT focuses on, is the simpler air parcel trajectories. And now when I explain PySPLIT to people, a question I get asked about 75% of the time is what is an air parcel? And an air parcel is a hypothetical small volume of air. It's small enough to be homogeneous, so we can think of it about the size of a meter cubed. So this is one of the higher profile applications of a particle dispersion simulation. So this is about 9 days after the Fukushima Daiichi nuclear incident, and it's showing the dispersion of cesium particles and their radioactivity. This is a trajectory simulation using forward trajectories starting at this location and moving forward in time for about 4 days. And in the academic realm, people use HYSPLIT for a variety of purposes as well. So this is from a relatively recent paper. It's actually a paleoclimate paper, but they use HYSPLIT to look at regional circulation at 3 different paleoclimate sites and use that to help their interpretation of the differences between these records. This is also a paleoclimate paper, but again, they use HYSPLIT to facilitate their interpretation of the record. So in this case, they're looking at the Indian summer monsoon, and they conclude that actual differences in the freshwater inputs to the source region is more important than changes in source region itself. And this is just an investigation of an extreme rainfall event. Here's a qualitative trajectory visualization and a more quantitative analysis of a long trajectory data during this rainfall event. And I've heard of a few other non-academic uses. I actually went to an official HYSPLIT workshop and met a couple who were interested in using HYSPLIT to help them in their ballooning hobby. So HYSPLIT can be used by everyone. There's an extremely low barrier to entry to this program, which I think we can all appreciate in the Python world. You can access it either online via the Ready interface, or you can download it to your PC and Mac. Now, since there is a low barrier to entry, there's a high variation in the quality of workflows that people use when they're interacting with HYSPLIT. And sometimes they're not very robust. This is the workflow that I used for an embarrassingly long amount of time before I learned about Python. And basically, I would sit there and generate the trajectories manually, copy-paste the data into Excel, click, drag, fill in cells, do calculations, plot using a circuitous route through a third-party program to Google Earth, and then cross my fingers and hope that it was what I wanted and what my advisor wanted, because it was about 3 weeks of active time. Eventually, I got this down to about 1 week, but it's a terrible workflow. It's not very repeatable. It's error-prone. And that's where PySPLIT comes in. So it only depends on NumPy, Matplotlib, and basemap. It's a very simple architecture with 5 classes, and it enables bulk trajectory generation, some very attractive visualizations, and overall a more efficient workflow. So, as I've said, the architecture is simple. The main class is the trajectory class. Each trajectory object represents a trajectory output by HYSPLIT. And the container for the trajectories is the not very creatively named trajectory group. They are iterable and additive. And if I were to put all of these trajectories in one trajectory group and then run a HYSPLIT clustering method on it, I would get the other 2 objects, which are clusters, which are special trajectory groups that have mean path data and only the trajectories assigned to it by HYSPLIT, and also a cluster group, which just contains the clusters. And so now with PySPLIT, my workflow, it's more straightforward, it's more repeatable, and let's take a look at that. So the first thing to do is to generate your trajectories. Basically, you give it the naming and directory information, the launch times and the launch locations, the duration and the direction of your trajectory simulations. And then there are a couple other keywords that trigger some special features. So one special feature triggered by the getReverse keyword is generating a trajectory that starts from the endpoint of a trajectory you just generated and runs it in the opposite direction. So in this example, I have an orange trajectory, and then I generate this red trajectory at its endpoint that runs forward in time. And we would hope that it would come back to the same place and close the loop, but it doesn't. And that indicates that the integration error in this trajectory is pretty bad, and we probably shouldn't use it. And that's compared to this pair, which closes the loop so well that you can't even distinguish them. This is a very good practice in HYSPLIT, but it's not performed as often as it should be because it's really a pain to do if you're doing HYSPLIT manually. It doubles your generation time, and it's a bunch more calculations that you have to do and add to your workload. Then the other special feature was the clip trajectory, and if you want to read more about that, you can look at my paper in the SciPy proceedings. And so once you generate your trajectories, you can load them all. I usually do everything in an IPython notebook. So this performs a non-recursive search in your directory for any trajectories matching this name. Bash wildcards are supported. And you get a trajectory group with all the trajectories matching that criteria. So the basic workflow, once you have your trajectory group, is to cycle through all the trajectories, perform some calculations, and based on the results of those calculations, sort them into new trajectory groups, and eventually winnow down your working set of trajectories into something that's manageable and has the information and criteria that you want to look at. Okay. And PySPLIT has a few nice canned visualization routines. One of the really nice things about this is that it accepts any base map. So you can fit it into your existing base map workflow, but it also includes this 5th class called map design, which allows you to quickly make nice looking base maps without really detracting from your attention from your trajectory workflow. And so all the PySPLIT maps that I'm showing have been made using this map design class and various degrees of customization. Okay. And now, because this workflow is so painless, you can resort, analyze trajectories, plot again as many times as you need without tearing your hair out. And to make this figure, the total active time was just one afternoon. And since all the data are easily exposed by PySPLIT, you can easily create custom products like this, which is a map of seasonal moisture uptakes using trajectories that arrive at one of 4 locations. And this is another custom product. It's basically just compacting all that data down into the weighted average uptake latitudes and uptake longitudes for those moisture uptakes. And so that's PySPLIT in a nutshell. You can get it on GitHub. You can look at this presentation again, also on GitHub, and you can read more about it in the SciPy proceedings.
We've got plenty of time for questions.
Though some of us never used HYSPLIT, but I've seen it a lot. Does it actually go out and grab the model data remotely? So does it actually, the executable runs on the computer and then it grabs the model data used to do the trajectory from an online source?
So if you run HYSPLIT on your PC, you have to have the data downloaded to your PC.
Okay, okay.
Yep.
Very cool.
I think it does have options for a couple of different source models, but maybe
Yeah.
not all of them. Like, if you're doing paleo stuff, you definitely need it.
Oh yeah, okay. Because that's not exactly real time.
Yeah.
So 2 questions. One, have you gotten the ARL folks interested in this at all? You know?
Well, I just posted this on GitHub earlier this week, and I haven't yet put out any publications using it. So there's really no way for them to know about it.
So
But
it's taking that long for you.
yeah, I started working on this a little less than 2 years ago, and actually started Python at the same time. So it's been a learning process.
My other question was, so are you fundamentally just generating HYSPLIT configuration files and then kicking it off, or are you working at a lower level with Java?
So what this does, it will, oops. So during the generation, it will generate new control files as needed. So basically, once a month, it will put all of the meteorology files needed for that month and like a week before and a week after. And then just run trajectories using those meteorology files and updating the altitude and time as necessary.
Is there what's taking all? It still takes quite a while to run. Is that what you said takes a half a day or something?
So it doesn't really take a long time to run. It can take a little bit of time to get the figures the way you want. But I did this in an afternoon.
What's the overnight component?
Oh, the overnight is the trajectory generation. So I think that the most I've ever set up to run at one time has been 60,000 trajectories, and that took about 24 hours.
So yeah, I guess it was. So is it running? Is it using parallel, or can it, or could it, or?
It probably. Actually, I'm not sure, because it's calling the HYSPLIT program that calculates them. So you'd have to set up some way for HYSPLIT itself to be multi-threaded.
Although it's kind of an embarrassingly parallel problem, isn't it? So if you looked at sort of running multiple instances of PySPLIT all at the same time,
I have not tried that.
maybe just wait until the next morning is a good way to go.
Yeah.
And just to add on to that, I do some trajectory modeling for ocean,
Mhm.
and I have 12 threads on the workstation I use, so I often will
Okay.
Some really basic poor man's parallelization like that, and it's just easy,
Yeah.
easy. As long as you don't go over on memory, that's always the trick.
Right.
But, that's usually easy.
Yeah. So once you have the trajectories, then actually doing the analyses and setting up the figures really doesn't take all that long in the grand scheme of things.